So in my case, I started with, I drew the line. Let's see what I did. I drew the line to cover these zeros, the three, all of them, that is lowise. Then I saw these three zeros which were lying on the same column. So I covered this. And then this zero here and this one, if I wanted, I could have still drawn a line going lowise. But I started with these two here. And then finally, this one, I could still be opting to draw a line lowise or vertically. And in my case, I did it vertically. So you see again, it doesn't matter. Are you drawing the lines horizontally or vertically? Are you covering the zeros lowise or column-wise? What matters is, are you seeing as many zeros as possible in that particular row or the column? Follow the descending order. But if there's only one zero to be covered, you can do it either lowise or even column-wise. Now, after we have drawn these lines, can you count? There are 4. So 4, is it the same as the number of assignments? We were to do 5 assignments. So again, the answer is a big no. What do? Iteration, remember. The process is iterative. We go back and we consider the smallest element in our already achieved table. And the smallest value in our table is which one? Let's identify the smallest figure here. The smallest value here is, which one is not covered and it is the smallest? 2. This is the smallest uncovered element, being 2 here. You subtract it from any other uncovered element. Okay, you see we are repeating our previous stages, huh? And you add it to any point of intersection. Like these 3 here, it's at the point of intersection. This 0 here is at the point of intersection. This one is also at the point of intersection. And we don't interfere with any element that is covered by only one line. So after I've done so, I achieve this table here. Again, we cover the zeros. We have said in the previous stage, we have identified the smallest element being 2 here. What do we do with that smallest uncovered element 2? You subtract it from any other uncovered element, including itself, and you add it to any element at the point of intersection, and don't interfere with any element covered by only one line. And after we have done so, this is the table we arrive at. Again, at this point, we cover the zeros. How have I covered my zeros? I have seen there's so many zeros falling on this particular row here, and I could as well do column-wise depending on the number of zeros I see in the table. So I saw these 3 zeros row-wise. 3 is the highest number of zeros that I can see column-wise or row-wise, and I could have as well covered them column-wise because I still have the 3 zeros here. So whichever you start with, it's okay. So let's assume we cover these zeros here, the column zeros, yeah? And you can see now the amount of zeros left to be covered. The highest that I see in a particular row or in a particular column are 2. Like in this row I have 2, in this row I have 2, in this other row I have 2. So depending on how quickly you want to cover the zeros, like in my case, I covered these 2 zeros here. I also covered these 2 zeros here. And I also covered these 2 zeros here. And you see all the zeros have already been covered. However, I could have as well drawn a line, yeah, going down to cover these 2 zeros. But still, I'll have to come back and I cover these 2 zeros here, and I cover this one and I cover that one. But I ask myself, is that the best way to which I can cover my zeros? because there were some zeros falling on the same line. Why did I not cover them like that? So the first thing you do is identify where possible you can cover as many zeros as possible. Remember, the procedure is you follow the descending order. So once we have covered our zeros, we now come back and we ask, how many lines have we used? And you can see I was using only one line. That one, number 2, 3, and 4. And the number of lines drawn to cover the zeros, again, are not equating to the number of assignments to be considered. So it means the solution is not optimal, and we cannot do our assignment at that particular point. So once we have noted that our solution is not optimal, we still go back to our previous stage. What do? We identify the smallest uncovered element again. You see we are doing what we call iteration, yeah? Then we add it to any point of intersection, and we subtract it from any uncovered element, yeah? And we don't interfere with an element covered by only one line. And the moment I did that, I realized that my smallest uncovered element so far from this table is 1, this one here. And we come and use that one to do the necessary. We add it to any point of intersection, like these 2 here, like this 5 here, and this 0 here. And we achieve this particular table here. As we subtract, remember this one from any uncovered element, but don't interfere with an element that was covered by only one line. And this is the table that I'll arrive at. Let's see, when we are now closing our zeros with some lines, what will happen? The lines to be drawn using our table here. Look at this. Where do we have as many zeros as possible? This column I have 3. This column I have 2. This row I have 2. And the rest are 1, 1, 1. So how do we do this? I'll start by covering the zeros where there are as many as possible. So all those can be covered by one line. Then I can go ahead and identify these 2 zeros here covered by one line. Then these others, this ones has got also 2, so I'll start with this. These others I can as well close them row-wise. There are 2 all of them, or even column-wise. Let me use columns, but you can as well do it row-wise. I could have as well done it like this. The moment I've covered these 3 zeros here, I go and I see these 2 zeros. So I could have opted to draw a line here to cover the 2 zeros. And then I cover this one alone, I cover this one alone, and I'll also come and cover this 0 here. But you realize that there's this 0 that also needs to be covered. So what do? This 0 and this 0 here were on the same column. Why can't I combine the 2 zeros? And that's why I've opted to draw the line vertically or column-wise. Now we count the number of lines covering the zeros. How many are they? 1, 2, 3, 4, 5. 5, the number of lines covering the zeros, equals to the number of assignments we wanted to do. The 5 aircrafts to be assigned to the 5 routes on the basis of one and only one route. Our solution is now optimal. And once you have realized that you have obtained optimality, you haven't answered the question. We wanted the optimal SAGE that can give us an optimal value in relation to the cost, in relation to now having the minimum cost. So what do? We come and do the assignment. And when you are doing the assignment, class, start with a unique 0. A unique 0 means where such an assignment can only be done in that particular route. Let's say our aircraft A can only go to route P. If that is special, in that you cannot assign it to any other route, start with that. Let's do it as per our case here. I've written down all my aircrafts, A up to E, and then I go back to this particular table. Once you have closed the zeros, we see where there's a unique 0. And perusing through, E can only be assigned to route Q. This 0 here is so unique in that E, alongside low E, there's no other 0. So that 0 is so unique. And so I'll go directly and assign E to Q. Don't start by, because you have written A, B, C, D up to E, you start with A. Go back to the table, find where there's some uniqueness. So we assign it to route, or rather we assign E to route Q. Then, is there any other unique 0? When you go to your table, you realize that an example aircraft A can be assigned to P and also R. And then you see R, yeah, is a route to which no other aircraft can actually take it. So again, this is some uniqueness depicted in our table. So you assign A to R. You leave P not to be assigned to be taken by aircraft A, because if you do, then R will lack an assignment. So you're assigning aircraft A to R because of the uniqueness nature of R. It can only be a given aircraft A. Okay? So you come and do that assignment. Then you can move to, for example, B. B can take which routes? P and Q. You can assign aircraft B to route P and Q. But now you had already assigned Q to E. Remember, on the basis of one and only one route in this case. So when you assign your B to Q, it means you have assigned route Q to, or rather to be taken by 2 aircrafts, which cannot happen in case of an assignment problem. So the only option left for B is to go route P. It has no other option. So indirectly you assign that to that particular route. Then we can go to C. C, we have 2 routes that it can be assigned to. That is P as well as S here. And if we were to do so, it would mean what? P has already been taken by B, so no assignment that is possible. And the only option that is left for C is now to take route S. So you do that assignment. And lastly, you now go to D. So if we were to assign D to S, because there's a possibility because of this 0 here, and we also have the chance of D being assigned to route T, you realize that D cannot be assigned to route S because that was the only option left for C to take. So you have to assign it to T. So you see, when you're doing the assignment, you are reasoning out. Before you are alive to say B can take this, you question why and how, okay? And then our aim was on minimization of the total cost. What do? We go back to our original table, the one that we were given from the past paper, and we read through the figures corresponding to how we have done our assignment. I've assigned A to route R. How much will it cost? 17 million. You pick the figures from the original table given. B, we have assigned it to route P. How much will it cost us? 8 million. And then later on, you sum over all the costs as far as the assignments to the various routes by your aircrafts now are concerned. And that becomes your optimal schedule, which gives you an optimal value that you can now comfortably call the minimum total cost. So that was how we were supposed to look at that particular problem.